we're going to spend a little time today talking about lines and angles and geometric shapes. So, lines, if you have two parallel lines, you mark them using arrows like this to show that they're going in the same direction. If you have several sets of parallel lines, you can use different numbers of arrows, like say this. Or even 3 arrows if you need. Usually though in a diagram you will not have more than 3 sets of parallel lines. And there is a point at which you can say this diagram is approximately to scale. In other words, angles that look bigger are actually bigger, or that lines that look like they're going in very different directions are in fact going in different directions. In that case, yeah, depending on convention, you could get away with one arrow, and then one arrow. But that requires disclaimers. And, well, what is this line that's crossing these two parallel lines? This line is known as the transverse, or transversal. Transverse or transversal. Okay. Now, what about these angles? Well, let's label them. 1, 2, 3, 4, 5, 6, 7, 8. Interior angles are inside the parallel line. So in other words, 3, angle 3, angle 4, angle 5, angle 6. This is taking us a little bit longer than I would like. So, how about we just say where the numbers are? In other words, exterior angles lie outside the parallel lines. Well, that's going to be 1, 2, 7, and 8. So it's where 1, 2, and 7, and 8 are. They're outside the parallel lines. Alternate interior angles are on the opposite sides of the transversal and inside the parallel lines. So in other words, we're talking about 3, 6, and the set 4, 5. When these lines are parallel, these alternating angles are equal. So if the alternating interior angles are equal, what does that say about the alternating exterior angles? So they're on opposite sides of the transverse and they're outside the parallel line. Well, aren't they equal to the corresponding opposing angle? This means that 1, 8 and 2, 7 are also equal pairs. They're alternate exterior angles. Corresponding angles are in the same position on the parallel lines in relation to the transversal. So 1 corresponds to 5. Because this line is parallel, they're in exactly the same directions. That means compared to this line, they form the exact same angle. Like say, oh, I'm going along a road, and I turn however many degrees to go along this road. Or I can turn the same amount of degrees to go along this exactly parallel road. These two go in the same direction forever because they're parallel. Okay. That means 1, 5, 2, 6, and so on. So 1, 5, 2, 6, 3, 7, and 4, 8. All right. Now let's talk a bit about line and angle relationships in general, like besides the two parallel lines being crossed by a transverse situation, which you'll have to deal with quite a lot. So let's draw or label most of these ourselves. So for parallel, we have A is parallel to B, or depending on notation, you can have these double vertical lines for parallel instead. And, well, the lines would look something like this. To mark them as being parallel, you would put arrows. going the same way. Perpendicular, you would use this symbol, little squarish symbol. And we would write this as, well, let's say this line is M and this line is N. This would be M is perpendicular to N. Opposite angles, you would have, say, A, B, C, D, and you would go angle A is equal to angle C, and angle B is equal to angle D. Now for adjacent angles, so angles that are next to each other but don't overlap, they share a side and a vertex but they don't overlap, you would say have angle X and Y, and then you would have maybe A, B, C or something, and you would say angle X plus angle Y equals angle A, B, C, perhaps. And these two would be adjacent angles. Complementary angles add up to 90 degrees, so you would be angle 1 and 2. Angle 1 plus angle 2 equals 90 degrees. Supplementary angles add up to 180 degrees. And this is, say, E and F. You would be like angle E plus angle F. Or you could be using letter codes like angle ABC or CBD equals 180 degrees. All right. Example. Suppose this figure is roughly to scale, which by that we mean angles that look larger are in fact larger, and the arrows are parallel. If one angle is 120 degrees, find all the others. Well, we have angles that are bigger than 90 degrees and angles that are smaller than 90 degrees. 120 degrees is obviously bigger, so this is going to be 120 degrees. 120 degrees because they're opposites, and alternating angles, you can put 120 here, or you can just go corresponding angles. 120 degrees. I, for one, do not recommend going with too many unnecessary rules to remember. Remember corresponding angles, and remember alternating interior angles, and everything else just kind of falls into place. Okay. What else? Well, there's also the angle sum here. Like if you're going one way and you turn, and then you turn again and go exactly the opposite way to where you started, you turn how far? 180 degrees. And, well, what else? This angle plus this angle is also 180 degrees. Yeah, that's a property of parallel lines. The interior angles that are on the same side of the transverse add up to 180 degrees. So, 60 degrees, 60 degrees, 60 degrees, 60 degrees. Now, exercises. Find the value of the other angle in each figure. Well, this, we use supplementary angles, because this is a straight angle. Also known as a straight line, this is 180 degrees. So 150, and the rest is 30 degrees. Obviously, this is not to scale. Most geometry diagrams are not, in fact, to scale, unless specifically labeled otherwise. This is complementary, so sum is 90 degrees. We have 40 degrees here, the rest must be 50 degrees. This is 52 degrees. The opposite angle must be 52 as well. And then, well, sum is 180 minus 52 gives us 128 degrees. Now let's say angles A and B are complementary. If A is 2x minus 10 and B is 3x plus 20, what is the measure of each angle? Well, sum of angle A and B is equal to 90 degrees. We're told this. Okay, so 2x minus 10 plus 3x plus 20. This is all in degree measure, by the way. Technically, this should be bracketed when you're first substituting in. But since it's a plus sign, there's no difference. So this is 90. And you end up with 5x plus 10 equals 90. 5x equals 80. X is equal to 16. And angle A is equal to 2 times 16 minus 10 equals 22 degrees. Angle B is equal to 3 times 16 plus 20. Or you could just subtract angle A from 90 degrees. Yeah? But this is really important. Try not to rely on prior steps as much as possible. So you substitute independently, and then you look at the final results and see if they fit the initial question's conditions. When you do that, you can make sure that you didn't get too bad of a calculation error. In other words, any calculation error whatsoever. So this is going to be 68 degrees. Because 3 times 16 is 48 plus 20. Okay. 68 plus 22 is 20 plus 70, so 90 degrees. Wonderful. This was correct. Moving on. We have congruent triangles. If you have two triangles that are the exact same, you label their corresponding sides, which are equal in length, with these little slashes across them. Now, usually you can see 1 slash, 2 slashes, 3 slashes, and very rarely in a diagram do you actually see 4 slashes. By the time you get to 4 slashes, usually people just start actually labeling the length. Right? Well, not really. I mean, you could be telling us that 2 pentagons are congruent. But really, by that point, you're probably going to be just like, because AB equals GH, BC equals HI. I is not very commonly used, but in geometry, but let's say it's used. And so on, and you list all the sides as being equal. And then you list all the angles as being equal. Therefore, A, B, C, D, E is congruent to whatever the corresponding letters are. Yeah. Okay. So if you have two angles with the same size and shape, so in other words, all the sides are equal, all the angles are equal. By the way, for triangles, all the sides being equal tells you that all the angles are equal. This is a property of triangles. You can't change the length of any side without changing either the length of the other sides or the angle, at least one of the angles. This is why triangles are structurally considered strong. If you have, like say, a square, it's easy to squish that into a parallelogram. Whereas a triangle will not have that problem if you're squeezing on it. Until, say, one of the sides just completely buckles it and gives out, or one of the joints fails. Yes, in a square you would also require joint failure, but joints are generally weaker than the structural members between said joints when you're doing construction. Okay, you would use arcs to indicate which angles are congruent. So you could have one arc, you could have two arcs, you could have, well, an arc with a little dash in it, or two dashes. So yeah, conventions vary somewhat. Just make sure that you match the corresponding type of arc when you're labeling a diagram. Now, in this diagram, we would, in symbols, because x corresponds to p, y corresponds to q, and z corresponds to r, we would be saying xz is congruent to pr. Now here, it's written like this. You could technically just say that they are equal, because if two line segments are of equal length, then they are congruent. They're not like shapes, okay? Because a line segment is one-dimensional. It just has a magnitude. You can turn it and so on, and be like, well, they're still congruent because they're still the same magnitude. This is because they're just a size. That's a one dimension. What direction they're going in doesn't matter to them. On the other hand, when we get to talking about vectors, this changes, but that's for much later. So the corresponding sides, you have to label them with the correct order of points. The corresponding points have to be labeled in the right orders. And, well, the angles, yeah, they are congruent, but you could also say that they're just equal angles. Because, once again, angles are just a measurement. All of these things you can say are just equal. But then, once you have these characteristics being equal, you can't say that, oh, triangle XYZ is equal to triangle PQR. You cannot do this. You have to say that they are congruent. Because these are just numbers. Like an angle measurement is just a number. The length of a line segment is just a number. But a shape is different. Now let's complete each congruent statement if we have some arbitrary, so in other words, some random triangle, DFH, which is congruent to a triangle PWZ, or PWZ. So angle F corresponds to, well, point F corresponds to point W. So this corresponds to point W. It's congruent to point angle W. Angle P, point P corresponds to point D. This is congruent to angle D. DH, well, D and H are corresponding to P and Z. Therefore, DH is congruent to PZ. ZW is congruent to, well, Z corresponds to H, W corresponds to F. Therefore, it's congruent to HF. When we move shapes around, for this level, we're moving them around on a coordinate plane. So a grid. We deal with translations, which are just move the shape, without turning or flipping it. Okay. What else do we deal with? We also deal with reflections, where we take the shape and flip it across an axis or the other axis. Okay. How do we do this? Well, if we're flipping across the x-axis, what happens? Well, we take all the vertices coordinates, and does it move horizontally? No. So, only the vertical coordinate, so the y coordinate, will change if we're flipping across the x-axis. Specifically, it becomes exactly the same amount, but in the opposite direction. So in other words, you flip the signs of each y coordinate. You multiply them by -1 if you're flipping across the x-axis. Remembering the rules, like, oh, to flip across x-axis, I have to multiply y-coordinate by -1, that's tedious, okay? So what do you do if you want to save yourself some effort? Visualize. Imagine actually doing this. What happens? Well, it's the same amount, but in the opposite direction, so the y-coordinate changes signs. Okay? And what happens if you're flipping across the y-axis? Well, does it move up or down? No. The x-coordinate of each vertex changes signs. Using this method is much easier than trying to remember separate rules for flipping across x or y axes. Now for scaling, well, we can make a figure bigger or smaller. Now, we need a point of reference to start this scaling. And this point of reference we call the center. This is not necessarily the origin, which is 0, 0, on your coordinate grid. You can find the displacement of each vertex from that point and then multiply by the scale factor. Look, if you start from 0, 0 and tell me that this arrow needs to be twice as big, it's pretty obvious that, oh, this point at 0, 0 just stays where it is if you use that as your center. And then the tip gets stretched out twice as far. Okay? So you stretch it out. Yeah, what did you do? You just multiplied where this was with respect to your original point. You took that, or you took the rise component and the run component, the x and y components, the x component and the y component, and you multiplied them. Okay. Wait a second. Who said just now that this point had to be 0, 0? This origin? This center that we're using? Oh, nobody. Therefore, for any shape, like say this shape here, if you want to blow it up to be twice as much, you calculate how far this is, horizontally and vertically, and then you go that far again, and you end up, say, with this. All right? That's scaling up to twice as much. We'll do an example of this soon enough. Now here, we have a reflection over the y-axis. PQRS, you have these vertices as below. And what are the vertices after the reflection? Let's say we didn't have this diagram to look at. So we didn't, draw the diagram and say, it must be here, here, and here, which we might have done back in, I don't know, grade 3 or something. So for P prime, P, -2, 2, reflect over Y, reflect over y-axis. This consists of, does reflecting it over the y-axis change its vertical position? So its y-coordinate? No. But the x-coordinate went from negative to positive, or vice versa. So this gives us P prime 2, 2. Q, negative 1, 2, gives us Q prime. And the x-axis coordinate inverts sine 1, 2. R, negative 1, negative 2. R prime, which is going to be 1, negative 2. S, negative 3, negative 1, gives rise to S prime, which is 3 and negative 1. And that's it. Now let's look at our diagram. Oh hey, it matches what we expected, which is that by flipping over the y-axis, the y-coordinate doesn't change, but the x-coordinate changes sign. Now, for exercises 1 to 3, use the diagram shown. The origin is 0, 0, and each grid is 1. So find the vertices after a translation of 5, 3. Well, A is, according to this diagram, this is negative 4, negative 4. It didn't say graph the figure after the translation. Okay, that's a little less trouble for us. So A is at negative 4, negative 1, and the translation is plus 5, 3. Now this isn't actually the sort of notation you'll be using when you actually use vectors. That you're going to be using square brackets to represent the change. But this is basically what we're thinking, okay? So we end up with A prime, which is 1, 2. Right. Now for B, which is negative 3, negative 1, that leads us to B prime, which is 2, 2. For C, which is negative 2, negative 2, we add 5 to the x-coordinate and 3 to the y-coordinate, and that gives us C prime. I'm going to close the table in a little bit, which is going to be at 3, 1. And D is at negative 1, negative 1, which is at D prime. And this is going to be 4, 2. And E, which is at negative 1, negative 3. This is going to be at E prime, which is negative 1 plus 5, so 4, 0. F is at negative 4, negative 3. Negative 4, negative 3, plus 5, 3 gives us F prime, which is at 1, 0. Alright, let's say we want to find the vertices after scaling to twice the size, with the center of scaling being negative 5, negative 4. Yeah, by the way, this whole center thing, depending on language, you could call it center of scaling, or various other words that mean the same thing. It's just some places think that having that versus the origin are too easy for students to get mixed up. So yeah, center of scaling is usually preferred, at least where I come from. So what happens is that we see that A is 1 grid over and 3 grids up from -5, -4. Okay? To project the whole thing to be twice as big, we need A to be twice as far away. So 2, 6 from there for A prime, or we end up with -3, 2. Now for B is -5, -4 plus 2 grids to the right, 3 grids up. 2 grids, 2, 3. So B prime is -5, -4 plus twice of 2, 3, which is equal to -5 plus 4, -1, -4 plus 6, 2. Right, C is 3 grids to the right and 2 grids up. -5, -4 plus 3 grids to the right and 2 grids up. So C prime is equal to -5, -4 plus twice of 3, 2. In other words, we're going to end up with 1, 0. Yeah, D, that's 4 grids over and 3 grids up. So twice as much. D prime is going to be -5, -4 plus twice of 4 grids over and 3 grids up. So, which is equal to -5 plus 8 is 3, -4 plus 6 is 2. And what about E and F? Well, E is 4 grids to the right and 1 grid up. So 8 grids to the right and 2 grids up will end up giving us -2. And F prime is going to be, it was 1 grid over and 1 grid up, therefore 2 grids over, 2 grids up will give us -3, -2. Yeah. Okay. As you can see, we abbreviated more and more as we kept going, because by this point, we either had understood how this worked, or we hadn't. And if you didn't, please go back and rewatch it to try to get the point. For quadrilaterals, quadrilaterals are polygons with 4 sides. They also have 4 vertices. The line segments in a quadrilateral, like any other polygon, intersect only at their endpoints. Now, a quadrilateral can be separated into 2 triangles. I mean, sure, it might seem intuitive for something like, say, a square or a rectangle to be separated into 2 triangles. And then you find, oh, all these angles, they add together. Each of these adds together to be 180 degrees. All of these added together must be 360 degrees. Okay. But what about something like this? Well, you can cut into two triangles like this. So, the sum of the measures of the internal angles of a quadrilateral is 360 degrees, even if one of those internal angles may be a reflex angle, so greater than 180 degrees. Let's find the missing angles in a quadrilateral with internal angles 120 degrees, 3x, 4x, and 8x. Okay. So, we know that 120 plus 3x plus 4x plus 8x equals 360 degrees. Yes, technically we should go with a degree symbol. Also up here, I guess. So, that means we end up with 15x equals 240 degrees. X is equal to, well, what happens when you divide this by 5? We end up with 48. And then we divide that by 3, and we get 16 degrees. So, 3x is equal to 48 degrees. 4x is equal to 64 degrees. And 8x is equal to 128 degrees. All right then. If we do a little bit of quick mental math, the 8 and the 4 go in and that becomes 60. So 60, 60, 120, 120. Okay, yep. Adds up all okay. Now, exercises. Find the missing angle measures in a quadrilateral with angles measuring 108, x, 3x, and 112 degrees. So we have 108 plus x plus 3x plus 112 equals 360. Therefore, 4x plus 220 equals 360. So x equals 35 degrees, and 3x is therefore equal to 105 degrees. Okay? Now, for a word problem, you should state the missing angles are 35 degrees and 105 degrees. But for our purposes, I'm going to omit them because I don't think you want to watch me write on the board any more than strictly necessary for you to understand the point. Just remember that for word problems, you should have a statement. So state your answer. If someone cuts a corner off a square and one of the obtuse internal angles formed is 133 degrees, how much is the other obtuse internal angle? Okay, guys, there's two ways to do this problem. So we cut a piece off, all right? And we know that one of these angles is 133 degrees. You can find this angle, which is going to be 180 minus 133. And that's going to give you 47 degrees. And that will give you this angle, which is 43 degrees. And then you can find that this angle is going to therefore be 137 degrees. What other method could you use? Well, for a quadrilateral, you can split the shape into two triangles. Alright then, what if you have a 5-sided polygon? You can split the shape into how many triangles? One more triangle. Because by adding an additional side, by making what used to be one side into two sides, you're adding a triangle. Okay. That means you can go for internal angle sum, which would leave you with 3 times 180 minus 270 minus 133. But that is for when we talk about polygons in general. So, what we would say here is C diagram. The other obtuse angle is derived from this diagram here. From 133 degrees, we got 47 degrees in removed triangle. And then the 43 degrees. And finally, the 137 degrees. Fun stuff. Yeah, polygons are simple closed figures that are formed by coplanar, so in the same flat surface, line segments. Like, suppose you have a shape that's like this. It's in 3 dimensions. They're not all on the same flat surface. Okay? This would not be a polygon. The line segments in a polygon are called sides, and they meet only at their endpoints. These points of intersection, these endpoints of the line segments, are called vertices. Polygons can be classified by the number of sides they have, and at 3 sides you have a triangle, 3 angles. That's the etymology. A quadrilateral is from 4 sides. It literally means 4 sides. Pentagon, hexagon, and so on. The gon is kind of just signifies that it's a polygon. Penta is the prefix for 5, hexa for 6, or hex for 6, hepta or hept for 7, oct or octa for 8, nona is for 9, and deca is for 10. Now, a diagonal is a line segment in a polygon that joins 2 non-consecutive vertices, forming triangles. You can use this property as and the interior angle sum of triangles to make your polygon into a bunch of triangles that don't have any angles that just add up redundantly with each other within the polygon. That would be bad. Okay? So they have the diagonals that you're counting, please don't cross them. So an interior angle is an angle inside a polygon, and the sum of the interior angles is n minus 2, where n is the number of sides, multiplied by 180 degrees. Think of a triangle. As you can see, by covering up one side at a time and adding 2 more sides each time, we can just keep on expanding the polygon with more triangles. So the interior angle sum is still going to be n minus 2 times 180 degrees. Because if you only have 2 sides, you can't have a polygon. You need at least 3 sides. A regular polygon is equilateral, all the sides are congruent, and equiangular, all the angles are congruent. Their measures are equal. So, what happens if you have more and more sides? Well, the irregular polygon will increasingly resemble a circle. Now let's find the measure of one interior angle of a regular 20gon. So in other words, there are 20 sides. Well, angle sum is going to be 20 minus 2 times 180 degrees. Okay. Angles are 20 minus 2 times 180 over 20, because you're dividing them among 20 different angles. Right. Cancels out. And we get 18 times 9, or 9 times 9, so 81 times 2, which is 162 degrees. Now let's classify some polygons and determine whether they appear to be regular or not. Here, how many sides do we have? 1, 2, 3, 4, 5, 6, 7. This is a heptagon. And it is not regular. Regular. This shape here, 1, 2, 3, 4, 5, 6, 7, 8 sides. And it is very visibly not all sides are equal, all angles are equal. So this is an octagon. And it is not regular or irregular. Preference for not regular versus irregular may differ. This is a quadrilateral. To be more specific, it looks like a square. A square is a regular quadrilateral. However, since we're supposed to state if it's regular or not, yeah, we kind of have to go quadrilateral and then regular. Alright, let's find the sum of the measures of the interior angles of each polygon. Now for a quadrilateral, sum equals 4 minus 2 times 180 degrees, which is equal to 360 degrees. Now for a nonagon, the sum is equal to 9, nona means 9, minus 2, so 7, times 180 degrees. So 1260 degrees. Alright then, what about a heptagon, which has 7 sides? Well, the sum is going to be equal to 7 minus 2 times 180 degrees, which is equal to 900 degrees. A 12gon, so a 12-sided polygon, that's going to be 12 minus 2 times 180 degrees, which is going to be equal to 1800 degrees. As you have more and more sides, your regular polygons will approach circles. However, there are plenty of irregular polygons to deal with. Now let's look at some areas of polygons. A parallelogram area is base times height. Why? I mean, we know that base times height is also the formula for, say, rectangles. Well, because these lines are parallel, let's say we take a rectangle and we slice a triangle off. Okay? And we slap that triangle onto the other end of the rectangle. That makes a parallelogram. Have we changed the height of that rectangle? No. Well, okay, it makes a different parallelogram, one without right angles, because a rectangle is a parallelogram. But anyway, did it change the height? No. Did it change the base length? No. Has the area changed? Well, we moved the triangle from here to there. No change. Yeah, okay, so what about triangle? That is 1/2 the base times height. The specific proof is a bit more complicated and we won't bother with it here. So, what about a trapezoid? A trapezoid's area is 1/2 height times the sum of the bases. You can see the trapezoid as two triangles, or you can go for congruent triangles using the midpoints of the sides. So here and here, okay? You can make congruent triangles. So there are two proofs here. You can do this, or you can just go A, B, H. Height is the same. Height times A times 1/2 is this triangle. Height times B times 1/2 is this triangle. Result, 1/2 height times A plus B in brackets. Yeah, so example 1. Find the area of a trapezoid with bases 3 centimeters and 10 centimeters and height 5 centimeters. The area is equal to 1/2 height times A plus B. Depending on which convention you follow, you could have A plus B over 2, so the average of A plus B, which, by the way, is derived from the congruent triangles method of derivation for this formula, times H. But this method is also, they're the same. So either way is good enough. It works. And you would have 1/2 times 5 times 3 plus 10. Therefore, 3 plus 10 is 13 times 5 gives us 65. And times 1/2 is 32.5. And this, the units would be centimeters squared. Now, for a triangle with base 4 centimeters and height 5 centimeters, the formula for the area is 1/2 base times height, which gives us 1/2 times 4 times 5. Therefore, this is going to be 10 centimeters squared. Well, square centimeters. Because 10 centimeters squared. Yeah, questions about brackets, guys? 10 square centimeters, not squared centimeters, on the other hand, offers no such... So a trapezoid with height 11 meters and bases 5 meters and 8 meters, area is equal to 1/2 height A plus B, so the two bases. And that's going to be 1/2 times 11 times 5 plus 8. The units here are meters squared, or square meters. Yeah, this was 5.5 by 13. 5 by 13 is 65. 65 plus 6.5. Yeah. Mental math is good. It's very useful, especially when you need to check your answers if you decided to use a calculator. Of course, usually I see people doing it the other way around, using the calculator to check their answers. To each his own. Anyway, a parallelogram with base 4 centimeters and height 8 centimeters. Area is equal to base times height for parallelograms, so that's going to be 4 by 8, which is equal to 32 centimeters squared. Or square centimeters. Alright, let's talk a bit about circles. Circles, they are not polygons. Even if they could, in a sense, be considered infinite-sided polygons. We don't consider them polygons for our purposes. They're a set of infinite points in a plane that are the same distance from a given point. Because what happens when you say you have a circle, the curve just plots the same distance from a point, and then you zoom in, and then you keep on zooming in, and you keep on zooming in. Do you ever find a point at which it stops being a curve and starts turning into lines? Segments? No. It is a set of infinite points that are the same distance from a given point. Circumference is a term for the perimeter of a circle. The circumference is pi multiplied by the diameter. Pi is a number they found for the ratio of the circumference to the diameter of circles. That's how pi is defined. C circumference is also equal to 2 pi r. You can find a pi button on scientific calculators. The area is pi r squared. Now, when you find the circumference of a circle with 2 kilometers radius, you would go, circumference is pi d, so pi multiplied by the diameter, or 2 pi r, which is equal to 2 pi times 2 kilometers, which is 4 pi kilometers. If your teacher wants you to show however many digits, or show to hundredths, or thousandths, or tenths, then you use a calculator and you actually multiply out or divide out what the pi's come out to. Approximately, because your calculator does not store the actual value of pi. It stores an approximation. Pi has no exact value. It is an infinite, non-repeating decimal. Now, for the area of a circle with 3 centimeters diameter, you would want area equals pi r squared, which is going to be pi times 1.5 squared, or 2.25 pi centimeters squared. So yeah, if your teacher wants approximate values, this is it. Or some sort of scientific calculator is it. Now let's do some exercises. Find the circumference and area of each circle if they're unknown. Give the exact values before rounding to the nearest tenth of a unit. Well then, circumference is equal to pi d, pi multiplied by diameter, so it's 10 pi meters. And that's approximately 31.4 meters. Okay, what's the area? Area is equal to pi r squared, which is equal to pi times 5 squared. Radius is half the diameter. The diameter is just going all the way across the circle at most. It's 2 radii that are end to end in opposite directions. The radius is from the center of the circle to the edge. Any edge. Okay, so any part of the edge. So this is 25 pi, and this is in meters squared, and that's approximately 25 times pi, 78.5 meters squared. Now, what if the radius was 6 centimeters? Well, then, C equals 2 pi r equals 2 pi times 6 equals 12 pi centimeters, which is approximately 12 times pi. So 37.7 centimeters. Now for area, pi r squared. So pi times 6 squared, 36 pi, and this is in centimeters squared, or square centimeters. So 36 times pi is approximately 113.1 centimeters squared. 30 centimeters circumference. Well, circumference is equal to 2 pi r. So we've got to find radius before we can find the area. That means 30 is equal to 2 pi r. R is equal to 15 over pi. And this is approximately 15 divided by pi, 4.8 centimeters. However, we have to use this exact value for the next step. You don't use approximations, otherwise you end up with cascading rounding error, which is no good. So, area equals pi r squared, which is equal to pi times 15 over pi squared, which leaves us with 225 over pi. And this is approximately 225 over pi, 71.6, and this is in centimeters squared. Okay, now let's say we have a 1,000, this is nanometers, not nautical miles. Nautical miles is NMI. Nanometers are very small things. But okay, the radius is 1,000 nanometers. Circumference is 2 pi r. That means 2,000 pi nanometers. And 2,000 times pi is approximately 6283.2 nanometers. What about the area? Area is equal to pi r squared, which is equal to pi times 1,000 squared. Therefore, it's 1,000,000 pi. And that's 3141592.7 approximately. Yeah. What are the units? Nanometers squared. As you can see, this is why a lot of the time teachers don't give questions that have very large radii or very many digits that you have to keep for your radii when you're doing areas. The answers get kind of long pretty fast. Okay, match each circles described in the column on the left with its corresponding measurement in the column on the right. Well, then we would use our calculator and go radius 5 units. Okay, r squared is 25 times pi. 78.53. Area is about 78.5. Circumference is about 31.4. Okay, so number 5 is C. Diameter 9 units. Well, 9 times pi gives us 28.274 and so on. Yeah, no, we're not looking for the circumference. That means 4.5 squared times pi, 63.6. Yeah, this is number 6. As you can see, I'm kind of leaving out the steps here in the middle here. It's recommended that when you first start doing this type of problems that you refrain from omitting steps until you have done quite a lot of them. However, I'm saving us all a little bit of time, and you're hearing me tell you what I am doing anyway. I am calculating the area and circumference for each of them and then matching them up. Diameter 12 units. 12 times pi, no, that's like 37.7, way off. So, that's probably D, but you can't be sure. Not always will these mix and match problems have every single choice actually get used. 6 squared times pi, 113.1. Yeah, this is number 7. And diameter 16 units. 16 times 3 is 48. 16 times 3.14159 and so on is going to be around 50-ish. Yeah, okay. So it's this thing. Now, what happens if we have complex shapes? Well, if we want to calculate for complex shapes, we gotta split it up into figures that we do know how to calculate, such as circles, area equals pi r squared, parallelograms, area equals base times height, triangles, 1/2 base times height, and trapezoids, area equals 1/2 height times the sum of the bases. Now suppose a trapezoid has height 5 centimeters with one parallel side being 15 centimeters and the other is 7. Suppose we think of this trapezoid as a parallelogram and a triangle. What is the area when calculated that way? So, one side is 15 centimeters and the other side is 7. And the height is 5 centimeters. We calculate it like this. Now this is 7, this is 7, this is 8. And this is 5. Why is this compatible with the formula for a trapezoid's area? I mean, we can see that the area is equal to base times height plus base 1 times height 1 plus 1/2 base 2, height 2. It's just that the heights are equal here. So the base for the parallelogram is 7. The height is 5 plus 1/2. The base is 15 minus 7, or 8. And the height is 5 again. 5 times 4 is 20. Okay. What part of this is compatible with the formula we know for trapezoids, where it's 1/2 height A plus B? Oh, wait a second. Where is this 8 coming from? This is 15 minus 7. Whoa, okay. So what we have here is height times A plus 1/2 B minus A times height. What happens here? Oh, HA minus 1/2 HA plus 1/2 HB. 1/2 HA plus 1/2 HB. Therefore, you end up with 1/2 HA plus 1/2 HB, or just 1/2 HA plus B. This is how it's compatible with the formula we learned earlier. But back to the question at hand, what is the area when calculated that way? The same as when we calculate it the other way, which is going to give us 55 centimeters squared. Okay, now suppose somebody decides to draw a gigantic stylized ice cream cone with a semicircle and a triangle. Okay, so this part is, these two sides are equal. This is 5 meters, and this whole thing across is 6 meters. That tells us that the radius is going to be 3 meters, and area is equal to 1/2 pi r squared, because it's a semicircle. It's half of a circle, plus 1/2 base times height. And this is going to be 1/2 pi times 3 squared plus 1/2 base, 1/2 base times height, which is 5. So you end up with 4.5 pi, or 9/2 pi, plus 5 times 3 is 15. And this is in square meters. However, this is not a very useful number, right? I mean, if you tell your gardener, oh, I need to mow 4.5 pi plus 15 square meters of lawn, yeah, I don't think this is going to go very well. So, what can we round it to? Well, depending on convention, mileage may vary on how you round. But 4.5 times pi plus 15, it's going to give you around 29.14 meters squared for the shape's area. Alright, let's find the area of each figure, round to the nearest tenth if necessary. A cross-section of a medical capsule, also known as a type of pill, looks like a rectangle with lengths 6 millimeters and width 4 millimeters. Okay, and the semicircles are attached to the ends, or at least it looks like this. Okay, how much area is this cross section? Well, two semicircles added together make for, when they're identical, a full circle. And here, you end up with area equals pi r squared. There, now I made it a little bit more technically correct. The best kind of correct. Anyway, plus base times height, because a rectangle is a parallelogram. Hurrah. So, this is going to be pi times the radius is 2 millimeters squared plus 4 millimeters by 6 millimeters. So this is going to be 4 pi plus 24 millimeters squared. Okay, the approximation would come out to 4 times pi plus 24, so about 36.57 or just 36.6 millimeters squared. Please consult local conventions on how many units to round to, or how many digits to round to, depending on, of course, the size of the units. For example, if you are doing, say, a word question that talks about machine parts, you might want to round to a few more digits than if you're doing a question about, say, a lawn you're mowing. Especially if you end up with, say, 10,231 square meters. And then you go, should I go 0.34 at the end? Does it actually matter after you already have like 10,000 square meters? No. Unlike, say, 1.3 versus 1 square kilometer, right? Okay. So how many digits you keep kind of depends on what you're using it for. Sometimes just apply a little bit of common sense, and also how many digits you've already kept before the decimal place. In other words, proportionately speaking, how far off are you going to be if you keep one less digit after the decimal place, considering how many you've already kept before it? A ring with inner radius 5 centimeters and outer radius 7 centimeters has how much area? Well, the area is equal to the outer radius. You have a disk of the outer radius and you subtract the disk in the middle. Pi r out squared minus pi r in squared. That's going to be pi times 7 squared minus pi times 5 squared. 49 pi minus 25 pi equals 24 pi. And this is going to be in centimeters squared. This is approximately 75.4 centimeters squared. Now a rhombus with base 10 centimeters and height 8 centimeters is cut out from the center of a square piece of paper with side length 20 centimeters. Okay, so the area is equal to, yes, the formula for squares is generally just written s squared, so side length squared, minus base times height. First, we should take a moment to think, is this question plausible? Well, the base is 10 centimeters, and since this rhombus isn't like negligibly tall, in other words, pretty much pinched flat, and almost 10 centimeters by 10 to either side, the square piece of paper can accommodate it comfortably. Okay, the question makes sense. So 20 squared minus 10 by 8 leaves you with 400 minus 80, which is 320 centimeters squared. Complex shapes, you add and subtract using shapes you already know how to calculate. Alright, well, that's it for this chapter. So, go do homework and practice problems, which I hope you've been doing between sections, by the way. And we'll see each other again next chapter.